So the heat capacity is a physical property that allows us to relate our enthalpies or our internal energy to changing temperatures. Let's now consider how the enthalpy is affected in systems in which the temperature is held constant, but the pressure is changing. Right? And so in this case, we can't really define a heat capacity because heat capacity is only looking at a system when the temperature is changing. Now we're looking at the system when we have a constant temperature. Okay? So once again, let's consider different states of matter. So once again, let's start with solids and liquids. So if we begin with a molar enthalpy, and we'll write out the definition of the molar enthalpy. So it's delta U squiggly plus P, and then V squiggly as well. Right, so I'm putting both of those things in here because now pressure is changing. So this thing is not constant. All right? But what is constant is the V squiggly. Right? And that's because since we're dealing with solids and liquids, that means we're dealing with incompressible states of matter. So their specific their molar volumes will not change. So pull out the V squiggly, and we have delta P. Another simplification we can make is with the internal energy. And that's because since we're at constant temperature, that means that we won't have a change in internal energy. Right? Because the internal energy only really changes if the temperature is changing. So because isothermal. And so for systems in which you have a constant temperature and a changing pressure, if you're dealing with a solid or liquid, your delta H is just going to be equal to the specific or the molar volume times your change in pressure. So it's a very nice and clean result. And so this is relevant if you're dealing with pumps or things like that, where the pump is isothermal, but clearly there's a change in pressure from the inlet and the outlet of the pump. All right? And as far as whether to get a good intuition or a good sense of the reason why delta U doesn't change when the temperature is isothermal, what I encourage you to do is to look at the steam tables. And you'll see that at various pressures, but if you're at the same temperature, your internal energy values are almost identical, or basically identical. Okay? So those were for compressible or incompressible states of matter. Let's now go to compressible states of matter. We'll begin with the ideal gas. Once again, start with the molar enthalpy is equal to the change in the internal energy plus delta PV. Alright? Internal energy, because we're dealing with a constant temperature system, this is going to be 0 because isothermal. And similar to what we did in the last video, because we're dealing with an ideal gas, we're going to say PV squiggly is equal to RT. Alright. And so our delta H is going to be equal to delta RT, but since R is a constant, we could pull it out, and we have delta H is equal to R delta T. But of course, we're dealing with systems in which we have a constant temperature, and so our delta T, that means our delta T is equal to 0, because we're dealing with an isothermal system. And so what pops out is that if you're dealing with an ideal gas at a constant temperature and you're just changing the pressure, your enthalpy will not change. your delta H is just going to be equal to 0. So that's what this means. So if you're dealing with problems in which you have an ideal gas and your system is changing pressure, but you're maintaining the same temperature, then your delta H is just going to be equal to 0. For the case where you have gases that aren't ideal, but they're close to it, generally, to make our life easier, engineers will just say that the change in internal energy and the change in the enthalpy, those are approximately equal to 0. So, for shorthand, anytime you deal with a gas and you're only changing the pressure in the system and not the temperature, you could assume or just apply these relationships, which just say that there's going to be no change in the internal energy or the enthalpy.